In classical mechanics, the dimension of space refers to the number of independent directions or coordinates required to specify the position of a point or particle in space. It provides a framework for describing the motion and configuration of physical systems. One definition of dimension of space. The dimension of space represents the minimum number of coordinates needed to uniquely identify the position of an object in a spatial system. Each dimension corresponds to a degree of freedom which allows the objects to move independently along that axis. Types of space dimensions in classical mechanics. Classical mechanics typically considers one, two, or three spatial dimensions. Um, One dimensional or 1D is when you have motion along a straight line. An example is a car moving on a straight road. Two dimensional or 2D it is motion in a plane. An example is projectile motion or motion on a flat surface. Three-dimensional or 3D can be described as motion in space, and an example is motion of a bird flying in the air or a planet orbiting the sun. Coordinate systems. The position of an object in space can be described using various coordinate systems. Cartesian coordinates, x, y, and z, most commonly used in classical mechanics, where each dimension is represented by an axis perpendicular to the others. Polar coordinates, r and theta, used in two-dimensional systems where motion is described by distance from a fixed point and an angle. Cylindrical coordinates, r, theta, and z, used for systems with cylindrical symmetry like pipes or rotating objects. Spherical coordinates r, theta, phi, used in three-dimensional systems with spherical symmetry like planetary motion. 4. Physical interpretation of dimensions. 1D space requires one coordinate to describe the position of a particle. Example, a train moving along a straight track. 2D space requires two coordinates, x and y, to describe the position of a particle. Example, a ball sliding on a flat surface. 3D space requires three coordinates, x, y, and z, to describe the position of a particle. For example, an airplane flying in the sky. 5. Time as an additional dimension. Though classical mechanics treats time separately, space-time in modern physics, like in Einstein's relativity, considers time as the fourth dimension. However, in classical mechanics, time is typically independent of space dimensions. 6. Significance of space dimensions. Degrees of freedom. Each dimension adds a degree of freedom influencing the complexity of the system's motion. Vector quantities. Quantities like velocity, acceleration, and force are represented as vectors with components in each dimension. Trajectory description. The motion of particles can be fully described by equations involving space dimensions. The dimension of space in classical mechanics is fundamental for describing the position, motion, and interactions of physical objects. Whether in one, two, or three dimensions, it provides the mathematical structure needed to model real-world physical systems. Understanding spatial dimensions is essential for solving problems in kinematics, dynamics, and other branches of classical mechanics.